Okay, hello. So on basic stratified structures in quantum information theory. So I'll tell you what we are trying to understand, what we have been trying to understand recently, and then the motivation why. So there'll be like first part, the first third, let's say, of the talk. About basic stratified structures, like some known results we've been trying to understand, and then I'll tell you about the motivation which connects it to the research I was partially speaking about last time. So yeah, it's been done together with Arsen Khvedelidze from Dubna as well, and Dimitar Mladenov, Stanislav Velkov from Bulgaria. So, yes, so I go back. Yeah, there's quite a huge delay. All right. Again, so there's a huge motivation coming from the application, from the industry side, quantum technologies, especially quantum computing, and not just. To study the properties, the features of the state space of an n-level quantum system, qubits, qubits especially, and to define it, an n-level quantum system. Just tell me, please, what's the pointer here? That's on the. It's this one. Yeah. So the object we are interested in is this set of complex n-by-n matrices, Hermitian, semi-positive trace 1, and the studies, and especially in the last 20 years, have taken mainly these three directions. So studying this set from the point of view of within a convex geometry. Professor Bogdan Mielnik was coming to a conference in Poland and took part several times. Well, he said that if you should remove everything and look from distance on quantum mechanics, the main feature that he would pick that remains is the convex structure of the set. From the point of view of topological properties and differential geometric properties. So we are interested in the underlying stratified structure of the set, because eventually the goal of the research would be to calculate metrics, especially we are interested in the Bures metric because of its special properties. I will define it later. On the whole stratified space, not just on separate strata. We would like to understand it as a complex object. So yeah, well, classical and quantum physics can be described both. So if we make this transition within the formalism of C-star algebras for self-adjoint elements, or we interpret as observables. And yeah, the question is to investigate whether this algebra admits like differential structures that we would be interested in. I think whether it would be to skip this, start with the definitions, come back here. I will do it actually 2 times here. So about stratified spaces, there'll be 2 definitions. First, yeah, so these what is a decomposition, an I decomposition? So if we have a set I, an I decomposition of a topological space X is then a locally finite collection of disjoint locally closed subsets of this set, one for each I, such that these two conditions are satisfied. So locally finite means that every point has a neighborhood which intersects with finitely many subsets. We'll call them PCs if I mean this is satisfied. And so locally closed subsets means that the subsets are an intersection of an open and closed subset. Yes, so the first condition is clear. We have this decomposition. The second is, we can call it the frontier condition, because if we have a non-empty intersection of a piece or of a subset with the closure of another one, if this is non-empty, then it implies that the first one has to lie in the frontier of the second one. So in this case, the sets Si are called the pieces of the decomposition, and such a topological space X, which is equipped with this I decomposition defined like this, will be called an I decomposed space. So that's the notion of a decomposition of a topological space. And yeah, so the second is stratification, and especially specifically the Whitney stratification. So what is that? So we use this notion of an I decomposition. So if again we have an X, a closed subset of a smooth manifold M, then an I decomposition of X is called Whitney stratification if each piece is a smooth embedded submanifold of this whole manifold M, and for all these indexes, the Whitney, the second Whitney condition is satisfied. There's first one as well, which actually follows from the second one. So yeah, in this case, we say that such a space is a Whitney stratified space, and we call the sets strata of this Whitney stratification. It turns out, if we speak now specifically about the state space Pn of n-level quantum systems, then we have we were interested in these three partitions. I don't say decompositions because yeah, the word partition here refers to all of them, but we cannot use the word decomposition as we defined it. Doesn't apply to all of them. So it turns out that if we make a partition by adjoint orbits, so this is not a decomposition because it's not locally finite. Then by orbit types, well, that's another way how to make this partition. But then we don't have a partition into smooth like submanifolds. And actually, so the one that we would be then interested in, and that was the subject of the work I spoke about last time, is the partition by this to the subsets of density matrices with fixed ranks. So it turns out that only the last of these partition, yeah, I shouldn't write decompositions because the first one is not. Partitions determines the Whitney stratification. So only the partition by subsets of density matrices with fixed rank is a Whitney stratification. well, what is the goal? And I'll speak about it now. So further on, to derive the Bures metric, the so-called Bures metric on each strata. So I will define this object on the next slide. So first of all, the Bures metric. Well, there are different metrics that are used to analyze this space. We want to put some conditions on them. Not the simplest metrics are not so nice in the sense that they lack some of the features that we want them to have. For example, the trace metric defined in this way is not Riemannian, although it's monotone as we want it to be. The Hilbert-Schmidt metric is Riemannian, but not monotone. And there are other metrics. One of them is the so-called Bures metric, which can be defined in several ways. Well, two main ways. One of them is through this expression. So if we have density matrices ρ1, ρ2, then the Bures distance from where the Bures metric can derive is defined like this. So trace of one and the other minus the so-called square root of the so-called fidelity defined through this not on the first side obviously symmetric expression. So yeah, so there is a Bures metric which has nice properties. Some other properties, nice properties as well, except for monotonicity, that is, it is monotone and Riemannian. And people have been using it quite a lot to analyze the properties of the set of density matrices n by n. So there have been found like explicit formulae for the Bures metric for special cases. So there are many articles on it, especially from the 90s. But because of the structure that I was speaking about in the beginning, one has to be more careful when one is calculating the metric for non-maximal rank density matrices, and this is what we have been trying to do. So yeah, so I mean there's another way how to define the Bures metric. Yes. So I've stated here some explicit solutions for the qubit and qubit case. So so if we have a qubit 2x2 matrix, we have two possibilities. So as for the rank 1, rank 2 matrices, so for the highest rank 2 in this case, we have a metric which we can write in this way. I won't comment much on this. So more a simple expression for the rank 1 states. For the qubit rank 3, 2, and 1 matrices, and yeah, so we have some explicit expressions for that as well. But what I would like to say is to come back and so where I think this is not the last version of the presentation, but okay. Okay, so I think I have to, I'll come back to here. Yes, yes, here. So, yeah, so as I said, the witness stratification is determined only by this partition of the set Pn, namely by the subset of density matrices of fixed ranks. So we did calculations for qubit, qtrit, also a little bit for quadrit, more demanding already calculations, but so we did this separately for all for each strata. So if we, so this P and K means yeah, so the set of matrices of n by n matrices of rank K. The thing is that we would like to consider this the metric as an object on the whole stratified space. Yeah, I think where is the expression? Must be here. Yeah, it goes very slowly with it. Yeah, anyway, so I will say it by words. Seems so we would have a union of so for every n we would have a union of these subsets. So for Pn we would have a union of Pn k with a sum over k from 1 to n, and so such an object would be the object of interest for the calculation of the Bures metric. So we have this Whitney stratification structure on the set, and we want to analyze from the different points of view that I mentioned in the beginning. So topology, differential geometry 1, the Bures metric on each strata, well, as a global object. Yes, I'm I'm sorry that really it seems that it's not the previous version of the presentation remained, so 2 slides are missing that I wanted to show. So it seems I'll have to stop here. There's yeah, there's a slide on the way how the Bures metric for rank deficiency states are calculated. So for a given row, for a given density matrix, so we consider this equation where G row is an unknown one form, which has to be calculated from this implicit equation, and the Bures metric is then determined through this expression. Yeah, so if one does this, one gets the explicit results that I have shown for a qubit and a qtrit. Yes. Yeah, I think I'll stop here. Yeah.
Okay. So let me clarify. The Bures metric, is it Martin Bures metric?
No, not yet.
Okay. Thank you.
But yeah, I must say, because it was really when I so the metric appeared probably first in an article from 1969 by Donald Bures. And well, I was curious because I have never met this this surname in other contexts than of Czechia, of the Czech Republic, as a surname. So I wrote to every Donald Bures I found on Facebook. There are like 5, yeah. So and about a year ago, and 2 weeks ago, one of them, the first one, replied and said, "Oh yeah, that's my father." So we've been in contact a little bit, yeah. So and he confirmed that he has Czech roots, yeah. So yeah.
It's a wonderful example how studying quantum mechanics then gets to find something about relatives and ancestry. Yeah. So,
Yeah, might be.
So yeah, it would be nice to determine the exact relationship. Yeah. So, okay, any questions? We just on time, so we have actually a couple of minutes. We won't even be behind. Afterwards, we have lunch. So this was something that you kind of ran into accidentally, or you
well, yeah. So that's so if you mean specifically the Bures metric, not so accidentally, because I said, as I've said, there are properties. I mean, it's generally considered to be one of the best metrics used in quantum information geometry. So this was not a big accident. As for the topic and on general on metrics and quantum information, a little bit, yes, that's true, yeah. Or maybe objections, because yeah, I'm here in front of an audience of mathematicians, and
that's right.
And the topology, and as a physicist, the notions from topology, from group theory, and yeah, there might be definitely objections.
Okay, so then we just on time. So let's thank speaker once again. And,